For decades, the way we've collectively talked about cancer has been incredibly linear.
Oh, definitely.
We treat it like a typo in a cellular blueprint. The narrative is always, you find the genetic mutation, you point to it on a chart, and you say, there it is, that rogue piece of code is what caused the tumor.
Right. It's a very comforting way to look at a terrifying disease.
Exactly, because it implies a really straightforward cause and effect. You find the typo, you fix the typo, you cure the patient.
And that is the foundation of how most people still conceptualize oncology today. Mutation equals cancer. The problem is, as our sequencing technology has gotten better, that simple equation has just completely fallen apart.
Which is honestly one of the most unsettling things I've read in a long time. Because you dive into the latest research, and we are about to go really deep on this, and you realize our bodies are actually these chaotic genetic mosaics.
Yeah, we are all walking around right now filled with cells that carry known, aggressive, cancer-associated mutations.
But they never become tumors. They just sit in our tissue, behaving like totally normal, healthy cells.
They are essentially harmless. I mean, the mutation is there, the typo is present, but the cell doesn't turn malignant. And that realization forces a massive shift in how we approach the disease. It means the genetic mutation is necessary, but it is not sufficient.
So what is the missing spark, right? What actually turns a harmless, mutated skin cell or lung cell into a malignant threat that can spread and kill you?
The answer to that is a biological shape-shifting process. It is a phenomenon called epithelial-to-mesenchymal transition, or EMT, and it is the central engine driving what oncologists now call tumor cell plasticity.
And that concept of plasticity is our mission for this deep dive. We are unpacking a phenomenal 2026 Nature Cancer Review by Jimenez Castaño and Nieto.
It's a brilliant paper.
It really is. We are going to deconstruct how cancer cells literally steal a normal, healthy biological program to disguise themselves, how they travel through your bloodstream, brainwash your immune system, and survive chemotherapy.
And, most importantly, we're going to look at the futuristic ways science is finally learning to hack this shape-shifting ability and use it against the cancer itself.
So if you've ever wondered why cancer is so hard to cure, or why a tumor can just suddenly return after years of remission, you need to understand EMT. This is the ultimate masterclass in cellular espionage.
It really shatters the idea of cancer as a static lump of bad cells.
Yeah.
To understand why tumors are so hard to eradicate, you really have to stop looking at the genetics and start looking at the disguise.
But before we get into the cancer of it all, we need to understand the disguise itself. EMT isn't a disease. It's a completely natural biological tool. We all have it. So what is EMT actually supposed to do when a tumor isn't hijacking it?
Well, go all the way back to when you were an embryo. You started as a very small, tightly packed cluster of cells. To form complex things like a heart, a nervous system, or a digestive tract, those cells had to physically move across the embryo. But epithelial cells, which are the building blocks of most of our tissues, they are not designed to move. They are rigidly glued to each other with strong cellular junctions, and they are firmly anchored to a basement membrane.
So imagine a brick wall for a second. The epithelial cells are the bricks, and they are completely locked in place by thick mortar. They are stationary by design.
Yes, perfect analogy. But to build an organ, you need those bricks to migrate. So EMT is the biological command that temporarily changes the nature of the cell. It dissolves the mortar.
Wow.
The cell loses its rigid structure, elongates, and gains a distinct front and back, which we call front-rear polarity, and it physically crawls away to a new location. Once it arrives, it reverses the process, locking back into a new brick wall to form a new organ.
It turns a stationary brick into a walking builder, and then back into a brick. That's incredible. And we don't just use this as embryos, right? The paper mentions adults use it for wound healing.
Exactly. If you get a deep paper cut, the epithelial cells at the edge of that wound sense the damage. They undergo a temporary EMT, they loosen up, crawl into the gap of the cut, and multiply to seal the tissue.
But there is a dark side to this even without cancer, isn't there?
There is. If that signal doesn't turn off, say you have chronic severe inflammation, the cells forget how to be bricks. They just keep crawling around and producing thick, fibrous proteins.
Which leads to organ fibrosis, like in the kidney.
Precisely.
Okay, so the mechanism is incredibly powerful. But who is giving the order? When you look under the hood of the cell, what is physically flipping the switch from brick to walker?
The orders come from a specific group of proteins called EMT transcription factors, or EMTTFs. You'll see families with names like snail, twist, ZEB, and PRRX.
Think of these as the master switches inside the cell's nucleus.
Right. When the cell detects an environmental stressor like a lack of oxygen, mechanical pressure, or chemical signals like TGF-beta from a wound, these transcription factors get activated. Their job is twofold. Shut down the genes that make the cells sticky and rigid, and turn on the genes that build a mobile, flexible internal skeleton.
I kept thinking of these transcription factors like a highly coordinated heist crew, because the paper makes it clear they don't all just rush the vault at once. It's sequential.
That's a great way to put it.
You have SNAL, which acts like the pioneer, the safecracker who sneaks in first, picks the lock, and turns off the basic epithelial alarm systems by repressing those genes. And then, once the door is cracked open, factors like TWIST or PRRX come in as the heavy muscle to induce the deep invasive mobility.
The sequence is everything, and because it's a step-by-step process, EMT isn't a simple on or off light switch. It's a sliding scale, a continuum. Cells can pause in the middle. We call these hybrid states, or partial EMT.
Meaning, a cell might drop half its mortar so it can move, but keep a few sticky junctions so it can hold hands with its neighbors while it travels.
Exactly.
Okay, let's do a quick recap for you listening. Point 1, epithelial means stationary brick, mesenchymal means mobile walker. Point 2, it's a sliding scale. And point 3, it's controlled by master switches like SNAL and TWIST.
Spot on.
So think about a time you got a deep paper cut. Your cells used EMT to heal that gap. But what happens when that exact same healing signal gets hijacked by a mutated cell?
Well, a single mutated cell is actually incredibly vulnerable on its own. The body has massive biological bottlenecks designed to destroy it.
Like what?
Usually when a cell realizes its DNA is corrupted, it triggers a process called oncogene-induced senescence. It essentially throws its hand up and permanently ages itself out of the ability to divide. Or the local immune system spots the mutation and assassinates the cell.
But if that mutated cell manages to activate EMT, it suddenly has a superpower.
It puts on a biochemical survival suit. Activating those EMT transcription factors, particularly SNAWALD, grants the mutated cell resistance to program death. It physically remodels the way the cell's DNA is folded, overriding those senescence alarms and causing genomic instability. It bridges the gap between a harmless mutation and an actively growing pre-tumor.
And the really alarming part of the review is what actually triggers that SNAL1 survival suit. It's not just random chance. It's intimately tied to chronic inflammation.
Exactly.
The things we know cause cancer, like smoking, severe air pollution, chronic tissue damage, they aren't just causing the genetic typos.
They are actively feeding the pre-tumor the very shape-shifting tools it needs to survive. The research shows that nicotine directly activates the TWIST transcription factor in lung cells through a pathway called STAT3 signaling.
Wow, just directly flipping the switch.
Yes, particulate matter from smog does the same thing. The toxic environment creates a chronic wound healing signal. The mutated cell hears that signal, activates EMT to quote-unquote heal the wound, and instead builds a tumor.
This changes everything about how I visualize a tumor, because once it's growing, it isn't just a uniform lump of identical bad cells. The researchers introduced this phenomenon called intratumoral heterogeneity, or IT.
Because EMT is that sliding scale we talked about, the tumor actually creates distinct functional neighborhoods.
The spatial organization is just mind-boggling. Let's look at the breast cancer models highlighted in the review. Researchers discovered that a single tumor can run 2 completely distinct EMT programs simultaneously, driven by different transcription factors in totally different physical locations.
Right, so on the outer edges of the tumor, you have the embryonic-like invasive cells. These are driven by the PRRX1 factor. They are shedding their brick-like nature completely. They are the frontline soldiers trying to break through the tissue and spread into the body.
But deep inside the core of the tumor, you have a totally different population. These cells run an adult-like inflammatory EMT program driven by SNAL1. And this is where my brain broke a little bit reading the paper, because if I'm understanding this right, the invasive PRRX1 cells on the outside are obviously the bad guys trying to spread the cancer, but the inflammatory SNA1 cells on the inside, they are actually associated with recruiting the body's own anti-tumor immune cells, like macrophages, into the tumor core.
That's exactly right.
It almost looks like the inside of the tumor is trying to destroy the outside of the tumor. Are these two populations fighting each other?
They are in a state of constant dynamic functional antagonism. It's a microscopic ecosystem balancing itself. The research proves that if you use a drug to selectively block the invasive PRX1 program on the edge of the tumor, You don't just stop the spreading.
You inadvertently remove the suppression on the core.
Yes, causing the inflammatory SNAL1 program to hyperactivate and flood the tumor with anti-tumor immune activity.
It's a complete paradox. If you attack the invasive cells, you boost the inflammatory cells. It explains perfectly why hitting a tumor with a single, highly targeted drug often fails. You aren't just killing cells, you are disrupting a delicately balanced ecosystem, and the tumor just shifts its shape to compensate.
And to truly see the lethal potential of that shape-shifting, we have to follow those invasive cells as they break out of the ecosystem and attempt to colonize the rest of the body. We have to look at metastasis.
Okay, let's do another quick recap. Mutations aren't enough, EMT is the survival suit, and tumors have distinct neighborhoods, invasive on the outside, inflammatory on the inside, constantly balancing each other.
Perfect summary.
So I have a question for you listening. If a tumor is made of different populations that dynamically balance each other, how do you think hitting it with a single, highly targeted drug will disrupt that ecosystem? It's a scary thought.
It really is. Now let's look at the journey through the bloodstream. These cells break off from the primary tumor and become circulating tumor cells, or CTCs.
Now, if I'm using standard logic, I would assume that the cells most capable of surviving the chaotic rapids of the bloodstream and spreading to a new organ would be the ones that have fully completed EMT. The most mesenchymal cells, the ultimate solo walkers.
It makes intuitive sense. But biology rarely follows our intuition. The most dangerous, highly metastatic cells in the blood are not the solo walkers. They are the hybrids.
The ones paused in the middle of the sliding scale.
Yes. They've lost enough of their rigid structure to detach and move, but they've retained just enough of their sticky epithelial properties to clump together. They travel through your veins in microscopic clusters, holding hands.
Which protects them.
Exactly. This cluster formation protects them from being ripped apart by sheer fluid force in the blood and shields them from immune patrols.
But the real plot twist happens when they finally land. Let's say this cluster of hybrid cells, or even a fully shapeshifted solo cell, slips into the tissue of your liver or your lungs. To actually colonize that organ and build a brand new tumor, they are faced with a massive problem. Fully mobile mesenchymal cells are virtually incapable of rapid cellular division. They can't multiply.
They are designed for travel, not for construction. To build a new tumor, they have to completely reverse their biological programming. They must undergo mesenchymal to epithelial transition. They have to throw away the disguise, turn back into rigid bricks, and start rapidly dividing to build the metastatic mass.
It is the ultimate sleeper agent strategy. You use the disguise, the EMT, to cross enemy lines, survive the hostile environment of the bloodstream, and infiltrate a new organ. But once you find a spot to build a base, you have to take off the disguise and go back to your original identity, MET-T, to start building.
The sleeper agent analogy is spot on, but it begs a terrifying question. What happens to the fully mesenchymal cells that manage to infiltrate an organ, but for whatever reason, cannot undergo MET-T? They can't take off the disguise.
They go into dormancy. They just go to sleep in the tissue.
They stop dividing entirely. They enter a state of suspended animation. And this is where we uncover one of the most tragic blind spots in modern medicine. Standard chemotherapy is designed to exploit rapid cellular division. It poisons cells that are actively multiplying.
Meaning the chemo sweeps through the body, utterly destroying the primary tumor and any rapidly growing metastases. The patient goes into remission, but the chemo completely ignores the dormant sleeper agents.
Right, because they aren't dividing. The poison doesn't register them. It spares them completely. And worse, the physical tissue trauma caused by the toxic chemotherapy can alter the local environment of the organ.
Right.
Years later, that environmental damage can act as an alarm clock, triggering the dormant cells to finally undergo MET, wake up, and initiate a massive, seemingly spontaneous relapse.
And the paper gets incredibly specific about how the local environment of different organs pulls the strings on these sleeper agents. It's not random. The microenvironment is the ultimate puppet master.
Take the bone marrow, a very common site for breast cancer metastasis. The blood vessels in the bone are lined with endothelial cells that express a specific surface protein called E-selectin. When a shape-shifted mobile cancer cell bumps into that E-selectin, it triggers a forced MA.
So the bone essentially forces the cancer cell to take off its disguise, anchoring it there and jump-starting a bone tumor.
Yes, but if that same cancer cell lands in the lungs, it encounters a totally different welcoming committee. In the lungs, you have resident immune cells, tissue macrophages that just naturally live there to keep things clean. These native macrophages secrete a molecule called TGF-beta2.
And for a dormant cancer cell, TGF-beta2 is like a lullaby. It forcefully keeps the cell in its dormant mesenchymal sleep state.
Until you get a bad lung infection, or you inhale toxic smoke. Suddenly, the lungs are inflamed. It panics and recruits brand new aggressive macrophages from the bone marrow to fight the infection. These new rookies show up, and they secrete a totally different molecule called versicin.
And versicin is the alarm clock. It disrupts the lullaby, forces the cancer cell to revert to its epithelial state, and suddenly, a dormant cell that has been sleeping peacefully for 5 years wakes up and begins rapidly dividing into a lung metastasis.
It is a microscopic turf war where the cancer just waits for our own body to make a mistake.
So time for another quick recap. Hybrid cells travel best. Full mesenchymal cells sleep. ME is required to build the new tumor base, and the local tissue environment pulls the strings.
Exactly right.
So knowing that chemotherapy might accidentally wake up dormant, shape-shifted cancer cells, how would you redesign treatment protocols to prevent a relapse? Just something to think about.
It's the million-dollar question in oncology right now.
But wait, let's talk about the immune system's role in all of this.
Yeah.
Because whether the cancer is waking up from dormancy or just arriving as a hybrid cluster, it is surrounded by the body's ultimate defense force. How on earth does EMT protect a cancer cell from being instantly devoured by white blood cells?
The immune evasion granted by EMT is arguably its most dangerous feature. It provides 2 layers of defense. The first is direct cell-autonomous immunoresistance. The very same transcription factors that make the cell mobile, like SNA1 and ZEB1, also force the cell to change the proteins on its outer surface.
Right, the paper talks about CD47. This is literally a surface protein that translates to "don't eat me." When a macrophage comes along to swallow the cancer cell flashes this CD47 badge, and the macrophage just backs off.
It's a literal invisibility cloak.
Yeah.
And they also weaponize other surface proteins. They dramatically spike levels of a molecule called PDL1. When an attacking T cell, the immune system's primary assassin, binds to PDL1, it triggers a chemical exhaustion pathway. The T cell literally gets too tired to kill the cancer cell and just gives up.
And they also downregulate MHC, right? Hiding their antigen name tags so they look like ghosts to the immune system. So they have a fake ID shield to stop the macrophages, and they carry an exhaustion gas to neutralize the T cells. That's the direct cloaking. But they also build what the authors call an active moat. And this blew my mind.
The microenvironmental immunoresistance. These shape-shifted mesenchymal cancer cells don't just hide. They actively secrete distress beacons, complex cocktails of things like TGF-beta, OPN, and IL-1-beta. These beacons float out into the surrounding tissue and intentionally attract specific types of immune cells, primarily regulatory T cells or TREGs and M2 macrophages.
But those are the immune cells designed to calm the body down. Normally, their job is to stop an immune response from going overboard. The cancer is literally recruiting them to act as a corrupt police force.
It brainwashes them. The cancer cell builds a physical barrier of corrupted immune cells around itself. This bodyguard squad actively suppresses any cytotoxic CD8 plus T cells from entering the area.
Wait, so the cancer cell isn't just hiding, it's actively brainwashing the local immune system to act as its personal bodyguard. And just a tiny fraction of these EMT cells can protect the whole tumor.
Yes. You don't need the whole tumor to undergo EMT to get this protection. Just a few shape-shifted cells can pump out enough distress beacons to build a moat that protects the entire tumor mass, including the normal non-shape-shifted cells.
Which perfectly explains why tumors with high EMT are notoriously stubbornly resistant to modern immunotherapy. You can pump a patient full of supercharged immune cells, but they just bounce off the moat.
It's a daunting defense. But this is exactly where the Jimenez, Castaño, and Nieto review shifts from terrifying to incredibly optimistic. Because once you understand the playbook of the shapeshifter, you can design weapons to specifically target the plasticity itself.
Okay, recap 4. EMT gives cancer cells CD47 shields, PD-L1 weapons, and the ability to recruit a corrupted immune bodyguard squad.
Yep.
So listener, if you were designing a drug to break this invisibility cloak, would you target the "don't eat me" shield on the cancer cell or try to reprogram the corrupted bodyguards?
Well, let's get into the actual counterattack strategies from the review. Because the old school method was just trying to build a traditional drug to jam the EMT master switches. But that failed.
Right, completely failed.
Traditional drugs are usually small molecules that look for a convenient pocket on a target protein to bind to and shut it down. But EMT transcription factors are essentially smooth. They lack those deep pockets. For decades, the pharmaceutical industry considered them completely undruggable.
Enter targeted protein degraders, specifically PROTACs. This is next-generation biochemical warfare. If you can't block the switch, you destroy it entirely.
PROTACs function like microscopic matchmakers. One end of the PROTAC molecule is designed to lightly grab onto the smooth EMT transcription factor. The other end is designed to grab onto the cell's natural garbage disposal unit, an enzyme called a ubiquitin ligase.
Ah, so it drags it to the trap.
Exactly. The PROTAC physically forces them together, and the cell shreds its own master switch.
It weaponizes the cell's own waste management system against the cancer. And the review also mentions TCIP's chemical inducers of proximity. Instead of trashing the switch, you rewire it. You take a transcription factor that normally turns genes off, physically glue it to an activator, and turn it into a self-destruct button, triggering apoptosis.
It is incredibly elegant, but my personal favorite therapeutic avenue from the review focuses not on the proteins, but on the physical cost of shapeshifting.
Yes, the ferroptosis vulnerability. Let's break this down because it requires an analogy. Think of a normal epithelial cell as wearing light, flexible clothing. But when it undergoes EMT and becomes a highly mobile mesenchymal cell, it has to put on heavy iron armor to survive the journey. And that armor is greased with very specific, highly flammable fats.
Biologically speaking, the process of EMT radically alters a cell's metabolism. To power its new mobility and survive the stress of moving, the cell pulls in massive amounts of intracellular iron. Simultaneously, it restructures its outer membrane, packing it with polyunsaturated fatty acids, or PUFAs, to make the membrane more fluid.
High iron and highly flammable fat. It gives them superpowers, but it creates a massive structural Achilles heel.
Exactly. It makes these shapeshifted cells uniquely hypersensitive to a very specific type of cell death called ferroptosis. Ferroptosis is essentially iron-dependent lipid peroxidation.
Cellular rusting.
Precisely. We can use specific drugs, like GPX4 inhibitors, to disable the cancer cell's antioxidant defenses. When we do that, the massive amounts of iron react with all those flammable PUFAs in the membrane, triggering a catastrophic chain reaction of rust. We essentially drop a rust bomb that selectively melts the mesenchymal cancer cells while leaving the normal, low-iron epithelial cells unharmed.
Dropping a rust bomb on the heavily armored sleeper agents, that is just unbelievable. But there is an even weirder approach in the paper. What if we don't try to kill them at all? What about cancer cell reprogramming?
Well, we talked about how these cells are highly plastic. They are in a state of biological identity crisis. Scientists have figured out how to exploit that confusion. Using specialized drugs, researchers have successfully taken highly aggressive plastic mesenchymal breast cancer cells and forced them to permanently differentiate into adipocytes.
Harmless fat cells. We are literally putting cancer cells into cellular witness protection. We just look at this lethal invasive cell and say, you know what, you're not a killer anymore. Your new name is Bob, and you just store fat.
It sounds like pure science fiction, but it has been proven to work in preclinical models. The tumor just turns into a small pocket of fat. They've even used viral vectors to force the plastic cancer cells to turn into dendritic cells, which are the very immune cells that train the body to hunt cancer.
We can force the tumor to become its own vaccine. And finally, we have to talk about the hardest targets, the hybrids. The ones holding hands in the bloodstream that cause the most metastasis. Because they share traits with both normal bricks and mobile walkers, they are incredibly hard to target without destroying healthy tissue.
Which is why researchers are developing logic-gated CAR T cells. CAR therapy already involved taking a patient's immune cells, engineering them in a lab to hunt a specific target, and putting them back in. But standard CAR T cells only look for one target.
Right. If they target an epithelial marker, they kill normal tissue. If they target a mesenchymal marker, they kill normal wound-healing cells.
So they use Boolean logic, specifically A and D gates. These next-generation CAR T cells are programmed with dual sensors. They will only fire their lethal payload if they bind to an epithelial tag A and D and mesenchymal tag on the exact same cell at the exact same time.
Sniper-level precision. It ignores the pure bricks, it ignores the pure walkers, and it only shoots the shape-shifting hybrids in the middle of the spectrum. This is a total paradigm shift. We aren't just blindly flooding the body with poison anymore. We are hacking their identity with PROTACs, rusting them from the inside out with ferroptosis, or forcing them into witness protection as fat cells.
It is the absolute bleeding edge of precision oncology. But the critical takeaway for the review is that no single one of these futuristic weapons will be a silver bullet.
Okay, final recap for the arsenal. We have PROTACs to trash the TFs, ferroptosis to rust them out, reprogramming to change their jobs, and logic gate RETs for sniper precision.
Spot on.
So to you listening, which of these strategies do you think holds the most promise? Hacking the cancer's identity or exploiting its iron-heavy armor?
It's going to require a mix, because the tumor is a dynamic ecosystem. If you hit it with just one thing, it shifts its shape again. The future of cancer treatment is sequential combination therapy. You use traditional chemotherapy or standard immunotherapy to wipe out the bulk of the rapidly dividing epithelial tumor.
But then knowing that the shape-shifting sleeper agent survived, you immediately follow up with a rust bomb or a PROTAC to sweep up the mesenchymal persister cells before they can establish a relapse.
Exactly. It moves the goalposts from managing a chaotic disease to outsmarting a predictable biological mechanism.
We have to stop viewing cancer as an invincible, static, genetic monster. It is a biological program. It's a piece of rogue software executing a sequence. And the better we understand the code, the better we can hack it, introduce vulnerabilities, and rewrite the ending for the patient.
That is the ultimate promise of understanding cellular plasticity.
Which brings me to one last mind bender for you to mull over as we wrap up this deep dive. We've spent all this time talking about how to creatively destroy these plastic cells, rust them out, or turn them into fat. But think about the very root of this. We know cancer uses EMT because it's fundamentally trying to tap into our ancient embryonic repair programs.
Right. It's trying to heal.
Exactly. It's a confused cell constantly trying to heal a wound that will never close. What if the ultimate cure isn't killing the cancer at all? What if one day we map this network so perfectly that we don't drop a bomb, we just supply the exact right biochemical signals to convince the tumor that the wound is finally healed? Turning off the EMT program permanently and quietly returning those chaotic cells to a peaceful state.
That would be the holy grail of oncology.
Keep questioning the blueprint. We'll see you on the next deep dive.